okay? But I was conscious of the fact that was sort of a last-minute plan because you went through the exercise nice and quickly, and I knew no, Ruby wasn't around and whatever. So I'm going to just recap on this and to repeat what I said at the end of yesterday's lesson and build upon it. Okay, so the next bit we're looking at is stationary points. Now, stationary points are, there are three types. You can either have a maximum, so a maximum point, like we've seen at IGCSE, or a minimum point, like we've seen at IGCSE, or we can have what's called a point of inflection, and I'll come back to that in a minute. Okay, now, so there are three types of stationary points, two of which are turning points. Okay, so three types of stationary points, of which the maximum and the minimum are turning points. Okay, so that's just the definitions. So it's useful to know, because if a question goes and says find the turning point, you know it's got to be either a maximum or a minimum. If the question says find a stationary point, you need to also consider a point of inflection. So I just want to talk you through this table again. Okay, what we know is that at any of these stationary points, for a split second, the gradient is zero. It is flat. It's flat at A, it's flat at O, it's flat at B. Okay, so f dash x, the differential, is zero. Okay, there is a zero gradient because it is flat at any of these stationary points. Now this bit here, this f dash x minus h, just means when you just go back a little bit to the left of the stationary point, and this f dash x plus h means we just go a little bit to the right of the stationary point. So just gathering our thoughts, at a maximum point, the gradient to the left is positive, is going uphill, and the gradient to the right is negative, is going downhill. So that's a maximum point. Let's go to a minimum point. Okay, so the minimum point's at B. So just to the left, the gradient's going downwards, so it's negative, and to the right, it's going upwards, so it's positive. So that explains the green, the yellow, the light blue, and the tan. Okay. Now, a point of inflection, and they could either be going downwards or upwards, but it's just going both downwards to the left and downwards to the right, or perhaps upwards to the left and upwards to the right. And as you can see, all that's changing is the rate of change. Okay, so we're going downwards, but at a decreasing rate until the origin, and then to the right, we're still going downwards, but at an increasing rate. So that's just really gathering our thoughts on what's going on for the three types of stationary points in terms of the gradients. Now, I didn't mention it yesterday, but it's an important point to make. These 2 points at A and B are what's called local maximum points and local minimum points, because clearly you can see it's the maximum and the minimum, but it's not the very biggest point. Okay, all these values over to the right-hand side as the line goes going upwards are clearly higher up than A. So A isn't going to be the maximum point on the whole of the graph. It's just the maximum point locally. Okay. Similarly with B, clearly that's the minimum over there, but there's loads of points over to the left as the line goes downwards, which are going to be less than that. Okay. So local maximum, local minimum. That's new terminology. Now, my mouse is just playing. There we go. Okay, so just moving on to the next slide, just we'll see what sort of lag we've got. Looking at the other screen, not too much of a lag. Okay, so example 16 is very straightforward. Okay, they've just gone and differentiated the curve. We're trying to find where the stationary point is, so we've set dy dx to equaling 0. We've then worked out that x is 2, and then we've substituted it into the original curve to work out the y value. So we've done plenty of that, so we know what the stationary point is. And then part B, you're not really going to get asked to do this, but you could prove whether it's a maximum or a minimum by just taking a coordinate a little bit to the left, a coordinate a little bit to the right. So do you see they've gone and done x equals 1.9. That's just slightly to the left of 2. So I've done x is 1.9, just circling it there. And we could see the gradient now is negative. They've then just done x is 2.1, substitute that into the differential, and saw that the gradient was 5.04, which is positive. Therefore, it must be a local minimum point. So that was example 16, pretty straightforward. Now, there is a more sophisticated way of deciding whether it's a maximum or a minimum, rather than just substituting points a little bit to the left and a little bit to the right. That's what we were practicing yesterday, okay? That d2y dx squared, okay, that allows us to work out whether a stationary point is a maximum or a minimum, okay? Because what that is doing is working out the rate of change of the gradient. So let's think about the one I've highlighted there in red, okay? If when we substitute into the second differential, we substitute it into f double dash a, okay, or d2y dx squared of a, if we get a value greater than 0, then it is a local minimum point. Now what we're saying there is the rate of change is increasing. So just picture that graph on the left. We're going downhill, so we've got a very steep negative gradient, then less of a steep negative gradient, still negative, but it's becoming less of a negative gradient, just going down the gradient, and it's getting less, and it's getting less, and it's getting less, and then it's nothing, and then it gets positive and positive and positive and positive. So the rate of change there is increasing all the time. That's why it's a local minimum. So whether the double differential is greater than 0, it's a local minimum. However, if the rate of change of the gradient is less than 0, then it's a maximum. So look at the one on the right, okay? So the gradient is positive, quite steep, still positive but less steep, still positive but less steep, 0, negative, and a growing negative, okay? So think of it as the rate of change of the gradient. If it's greater than 0, minimum, less than 0, a maximum, okay? So another way, just to sort of a shortcut way, okay, just think about what's happening on the second half of the graph, if you like. So it's the second differential, so just consider the second half of the graph. So on that first one there, the second half of the graph is going upwards, is greater than 0, that's when it was greater than 0. On the second one, okay, where it's less than 0, the second half of the gradient is going downwards. That's the local maximum, okay? So however you think, you just got to learn that if the second differential is greater than 0, it's a minimum. The second differential, when you substitute the value in, is less, the x value in is less than 0, it's a maximum. And so the hint, like I was saying, the second differential tells you the rate of change of the gradient function. Right, so we then have an example, which again I won't bore you with. You were excellent yesterday at just doing the differentiating. Let's just cut to the chase and look at the bit in green at the bottom. For part B, find d2y dx squared and use it to determine the nature of the stationary points. So we've just gone and substituted in. So we've got the one in green. I've missed the one above it, haven't I? The one above it. When x was 1. We substituted into that purple bit there. We've substituted the x value in. We got a negative number, negative 18. That is less than 0. Therefore, the coordinate 117 was a local maximum. And then our second stationary point that we've worked out at the top. Okay, the second one was, whoops, I wanted to do that in green. The second one at the top, when we worked out 4 minus 10. Substitute the 4 into the second differential. We got a value that was greater than 18. Clearly 18 is greater than 0. Therefore 4 minus 10 is a local minimum point. And again, similar with example 18. Let's just go down to B. When we substituted it into the second differential, we got a negative when x was minus a third. So that is a maximum. Then when we substituted in our second stationary point, we substituted in a third, we got a positive d2y dx squared. Therefore, that was a local minimum. And then they just sketched it. So that's it, guys. So what I want us to do, exercise 12I, but I want you to leave question 1. I want you to leave question 2. So I want you to get stuck in from question 3 onwards, please. All right, so we're going to start on question 3, and I've only copied and pasted them so far, so I'm going to be working, doing these at the same time as you. So that's it on the teaching front, guys. So if we could just crack on with 12i from question 3 onwards. I'm just keep your camera off for a second while I stop the recording. Stop recording. Stop recording.